Alright, let's continue with part 2 of the probability introduction. We just talked about the area model of probability, and now we're going to talk about probability tree diagrams. This is probably something you might have seen before, but let's look at it closer. Okay, your teacher challenges you to a spinner game. You spin 2 spinners with the probabilities listed at right. The first letter comes from spinner 1, and the second letter comes from spinner 2. If the letters can form a 2-letter English word, you win. Otherwise, the teacher wins. Instead of using an area model for this scenario, we can use a tree diagram. So let's first make the tree diagram of the possibilities, and then we will use that to answer our questions. So first, we have a spinner that has the letters I, A, and U. So if I spin the spinner, I can either spin the letter I, A, or U. Those are the 3 possibilities. Now on the branches of the tree diagram, we are going to write the probability of each letter. So I is half of the spinner, so that has a 1/2 chance. We have a 1/3 chance of spinning an A and a 1/6 chance of spinning a U. So we're going to add those to the branches of our tree diagram. Then, after spinning spinner 1 and I spin spinner 2, I have the option of landing on a T or an F each time. So for a tree diagram, to count the number of possible outcomes, you always count the last branches. So 1, 2, 3, 4, 5, 6. There are 6 total outcomes, but not all of them make words. Just a reminder there. To spin a T, it has a 1/4 chance because it's 1/4 of the circle. And for F, there's a 3 out of 4 chances. So T, we have 1/4. 3/4, 1/4, 3/4, 1/4, 3/4, and so on. So we can use this diagram now to answer some of the questions. So we have 6 total events, so let's talk about those. We're just organizing our information. So we have an event, and then we have the probability of that event. So event number 1, if you follow the trail, if I spin an I, then a T. You multiply through the branches. So the probability of spinning an I, then spinning a T is 1/2 times 1/4, which is 1/8. So if we continue that process, the next event would be an IF, which is 1/2 times 3/4, which is 3/8. The next event, spinning A, T, 1/3 times 1/4, which is 1/12. Next event, AF, 1/3 times 3/4, which is 3/12. Next event, UT, 1/6 times 1/4 equals 1/24. Last but not least, a UF, spinning a U, then spinning an F, 1/6 times 3/4, which is equal to 3/24, which equals 1/8. Now something to remember is that these all must add up to 1. So the total must always add up to 1 for all the possible outcomes. Okay, so let's look at the questions and figure that out. What is the probability from spinning spinner 1 and then spinning spinner 2 of creating a word? Well, let's look. Which ones create a word? it is a word, at is a word, and if is a word. So we want to know the probability of spinning I, then a T, plus the probability of spinning an I, then an F, plus the probability of spinning an A, then a T. That's equal to 1/8 plus 3/8 plus 1/12, which is equal to 7/12. So the probability of spinning a word from spinner 1 and spinner 2 is 7 out of 12. What's the probability of not creating a word? Well, let's look at this. If my probability of creating a word, well, let's see, of not creating a word. All right, so AF, UT, UF. So that's 3 over 12 plus 1 over 24 plus 1 over 8. So the probability of not creating a word is equal to 10 over 24, which is equal to 5 over 12. Is this game fair? Explain. So let's look. I have a 5 out of 12 chance of not creating a word, and I have a 7 out of 12 chance of creating a word. And it says, if the letters form a word, then you win, otherwise the teacher wins. So it's not fair because the probabilities of of creating a word is not the same as the probability of creating a word. If they were the same, then it would be fair, but since they are not the same, it is not fair. Okay, let's look at another example. Ryan has a pet rat named Romeo, and he boasts that it is the smartest rat in the country. Sammy overheard Ryan at the county fair claiming that Romeo could learn to run a particular maze and find cheese at the end. I don't think Romeo is that smart, declares Sammy. I think the rat just chooses a random path and goes through the maze. Ryan has built a maze with the floor plan shown at right. In addition, he has placed some cheese in an airtight container, so Romeo can't smell the cheese in room A. Suppose that every time Romeo reaches a split in the maze, he is equally likely to choose any of the paths in front of him. What is the probability that Romeo will find the cheese? Well, let's first of all take a look at this and redraw it into a tree diagram. This already kind of looks like a tree diagram, so I'm just going to kind of recreate it. So in the very first intersection here, Romeo has 3 options. So I drew the first 3 branches. Then once he gets here, he then has 3 options. 1, 2, 3. If he goes straight, he's straight into room A. Then he goes here and has 2 options. So I'm just kind of redrawing what his options are here. Now, Romeo comes to his first intersection. If he is equally likely to choose any of the doors, and there's 3 doors, each door is going to have a 1/3 chance of the first intersection. Then he comes to this next intersection. Say he chooses the left route. He has another 1/3 chance of choosing the next path. And then if he went this way, he has a 1/2 chance of choosing each one because there's 2 total options. Now let's label the doors. These 2 lead to door B. This leads to door A. This leads to door A. This leads to door A. And this one down here leads to door B. So all I've done is kind of redraw the situation. Now it asks, what is the probability that he will find the cheese in room A? So let's highlight all the paths to room A. We have this path as one of the options. We have him picking the first path straight to door A as one of the options. And we also have this path to door A as one of the options. So there are three options for him to choose There are three paths for him to choose to get to door A. So let's find the probability of each. Path 1 to door A. The probability of getting there is 1/3 times 1/3. And we're going to add that to path 2. If he picks this path 2, he goes straight in, and that's a 1/3 chance. Path 3 is 1/3 times 1/2. So these are the three paths to room A. So that's 1/9 plus 1/3 plus 1/6. We got to get a common denominator here, which is going to be 18. So I'm going to multiply that by 2. Multiply this by 6. Multiply this by 3. So we get 2 over 18 plus 6 over 18 plus 3 over 18, which is 11 over 18. Probability of Romeo getting to the room A with the cheese is 11 over 18. So again, with tree diagrams, on each branch you label the probability of getting to that outcome, and to go through a tree diagram you multiply the probabilities together for different events. Okay, let's apply this probability now. If Romeo were to move through the maze randomly, how many out of 100 attempts would you expect Romeo to end up in room A? How many times would you expect him to end up in room B? So all we're going to do is take 100 times the probability of getting into room A, which is equal to 100 times 11 over 18, which is what we just found, which is approximately 61.1. So out of 100 times, we would estimate that 61 times he would make it to room A, which means 100 minus 61 equals 39 times he would make it to room B. The total is 100, and we found out he has about a 61% chance out of 100 to get into room A. He would get there about 61 times out of 100. Alright, let's look at some examples. So this is kind of similar to the last problem, but let's see what it's asking. Always skeptical, Sammy says, if Romeo really can learn, he ought to be able to figure out how to run this new maze I've designed. Examine Sammy's maze at right. Sketch the tree diagram to better see the probabilities for each path. Okay, so we're going to re-sketch the tree diagram and then answer the question that it's asked. So once again, we come up and we have the first intersection. There's only two paths to choose from the first intersection. I'm going to draw 2 branches there. Then let's say he chooses the left side. We come up to this intersection now. Romeo now has 3 options. So we're going to draw 3 branches here. The first 2 branches go to room A, and the third, it looks like, goes to B. Okay, let's say that first time here he chose this way. Now, at this intersection, he has 2 options. So this one you gotta kind of be careful. Once he gets here, this row went straight to B. Once he gets here, he can either go straight again or break off again into room C. So you gotta be careful of that last intersection right there. Okay. So let's fill in the probabilities. The first intersection, there's 2, so he has a 50-50 chance of choosing either side. Then when he gets up here, if he chooses the left side first, he has a 1/3 chance of picking all 3 of these. We got to be careful because right here he has a 1/2 chance of choosing either of these, but he also has another 1/2 chance here once he gets to that intersection. Got to be very careful. Each intersection has an equally likely chance of being chosen. Okay, so let's see what it says now. To give Romeo the best chance of finding the cheese, in which room should the cheese be placed? Justify your answer. So we are finding that which room has the highest probability of him going into. So we need to actually find the probability of him making it into each room. So let's just go ahead and make a table of all the options, and then we will be able to pick our answer at the end. Alright, so one side is going to be the event, and one side is going to be our probability. Alright, so first event. So each event is going to be each way he can go to get to a room, and we're going to calculate the probabilities of all of those. So the first event is going to be getting to A. So the probability of getting to room A the first way is going to be 1/2 times 1/3. Which is equal to 1/6. Okay, the second event is getting to A again, but now using this path, 1/2 times 1/3 again. The next option is getting to room B, 1/2 times 1/3. Whoops. Okay, and now we have him getting to room B again, but going this way, straight, 1/2 times 1/2 times 1/2. Which is equal to 1/8. Then we have him going to room C this way. That is also 1/2 times 1/2 times 1/2, which is 1/8. And then him getting to room C the final way, then this way, which is just 1/2 times 1/2, 1/4. So the probability of getting to A is equal to 1/6 plus 1/6, which is 2/6, which is about 33%. The probability of him getting to room B is 1/6 plus 1/8, which is approximately 0.292. The probability of getting hit to room C is equal to 1/4 plus 1/8, which is 3/8, which is about 0.375. So if we look at our 3 final answers of each room, he has the largest probability of getting to room C. So room C has the highest possibility. So he should place the cheese in room C to give Romeo the best chance. And last but not least, one more scenario. You are off to soccer and love playing goalkeeper, but that depends on who is coach for the match. With Coach Sam, you have 50% chance of being goalkeeper. With Coach Alex, you have a 30% chance of being goalkeeper. Sam is coach more often than Alex, about 6 out of every 10 games. Use a tree diagram to determine the probability that you will be goalkeeper today. Okay, so let's draw a tree diagram. So it says about 6 out of every 10 games, Sam is the coach more than Alex. Okay, so first we need to figure out who's going to be the coach, Sam or Alex. There's 2 options for the coach. It says 6 out of every 10 games, Sam is the coach. So 6 out of 10 is about 60%. So 60% of the time Sam is the coach, 40% of the time Alex is the coach. Let's read what it says. If Sam is the coach, you have a 50% chance of being goalkeeper. So if Sam's a coach, I have a 50% chance of being a goalie and a 50% chance of not being goalie. If Alex is the coach, you have a 30% chance of being goalie. So that means you have a 70% chance of not being goalie. So let's use it to determine if you're going to be the goalie or not. Well, there's 2 probabilities here. There's 2 outcomes that you're the goalie. And they go this way and that way. So the first probability of you being goalie is 0.6 times 0.5. That's if Sam's the coach and he picks you to be goalie. So that first probability is 0.30. The second probability would be 0.4 times 0.30, which is 0.12. Both of those outcomes lead you to being goalie. So either of these probabilities would lead you there. So I'm going to add them together, which is 0.42. You have a 42% chance of being goalie. Alright, that's it for that. You have a 9.1 homework to go with this and a 9.1 quiz on Schoology to complete. Hope you